Welcome to lesson 4.7.1, and in this lesson we are going to be working with trigonometric identities. Determine a general expression for the non-permissible values in degrees for the following: a. Cotangent of x over 1 minus sine of x, and b. 1 plus sine squared of x divided by 1 minus sine squared of x.
Okay, so this is an interesting question here when we talk about the non-permissibles. Because there's something here that you got to remember as you're working through a problem like this. A couple of things. First of all, non-permissibles come from the denominator, okay, being equivalent to 0. We can't let that happen, right? We cannot let the denominator equal to 0. Now, having said that, when we talk about trigonometry, there are only two trig functions that do not bring their own set of non-permissibles with them. That's sine and cosine. Tangent has a denominator. Cotangent has a denominator, so does cosecant and secant. They've all got denominators, and so they all come with their own set of non-permissibles. So when we take a look at this first question right here, cotangent of x over 1 minus sine of x, the very first thing that we might want to do here is go and figure out for what values of x does 1 minus sine of x become 0. And bring the sine of x over, and we'll get that. Well, that's going to occur when the sine of x is equal to 1. And now let's think about that. When does the sine of x go to 1? When does sine take on a value of 1? Well, you might think about the unit circle. Think about the fact that the sine ratio is always related to the y-coordinate of any point on the terminal arm. Where does that go to 1? Well, it's going to go to 1 at 90 degrees. Okay, so in other words here, I cannot let x become 90 degrees or 90 degrees plus any multiple of 360. Okay, so I can't let it point up, but even if it wraps around, I can't let it do that. Okay, anytime it wraps all the way around, and again is pointing right up along the positive y-axis, that's a non-permissible. So that's one set of non-permissibles here. The other set of non-permissibles comes from cotangent itself. Okay, remember that cotangent of x is going to equal the cosine of x divided by the sine of x. Which means, in addition to this, I cannot allow the sine of x to go to 0. Now, where does the sine of an angle go to 0? Think about that unit circle. Where is the y-coordinate? Okay, along that terminal arm, where does the y-coordinate go to 0? And the answer is along the x-axis, either the positive x-axis or the negative x-axis. Which means I cannot allow x to be any multiple of 180 degrees. I was just about to do radians there. Okay, I hesitated a second there because I was just about to put a pi there. But I can't let x be any multiple of 180 degrees, because if it is, then the sine is going to go to 0, and I can't let that happen because that makes the cotangent undefined. So here are my two sets of non-permissibles. Okay, let's go over here and look at the next one. 1 plus sine squared of x, okay, and then 1 minus the sine squared of x. Now, there's a couple of ways that we can take a look at this here, but notice that this particular expression here does not have the tangent, cotangent, cosecant, or secant in it. So all I have to do in this case is focus my attention on the denominator. So that's 1 minus the sine squared of x. I can't let that equal 0. Okay, if it equals 0, then I'm going to run into some problems here. So I'm going to figure out what the restrictions are. So I'll bring the sine over. Now this is just one way of doing it. Another way of doing this is to understand that 1 minus the sine squared is going to be cosine squared. Okay, because that's an identity, and that's obviously the direction we're going here. But I don't need to do that right now. I can bring that sine squared over. And I'm really choosing to do it this way because there's something here that I want to make sure that you're doing correctly here. If I put the cosine squared in there, you likely wouldn't run into this particular issue, but there is an issue here. When you take the square root of both sides, remember that the square root of 1 in this case, when I'm solving an equation like this, the issue here is that I cannot let sine equal positive or negative 1. Okay, there are two solutions here. Okay, if sine is positive 1, when you square it, you'll get 1. If sine is negative 1, when you square it, you'll get positive 1. So neither one of those two is acceptable. Now, I got to think, okay, well, where does that occur? Where does sine become positive 1? Well, we just did a question like that. I know that's at 90 degrees. Where does sine go to negative 1? Well, it's at the other end of that unit circle. It's going to be pointing down at 270. So what I'm going to say here is I cannot allow x to be 90 degrees or 270 degrees, and I might add to that just multiples of 360, integer multiples of 360. And that's a perfectly fine answer. Nothing wrong with that. But I can write that a little bit better. Okay, we could say, or I could write it like this. Because 90 and 270 differ by 180, I could simply say that x can't be equal to 90 degrees plus multiples of 180 degrees, and that'll actually cover 270, and then it'll cover all the same set of angles that we're expressing right here. Either one of those is okay. There's a little bit of redundancy here. This is a much cleaner way of writing it. It shouldn't really matter.
Consider the identity cos x plus the tangent of x times the sine of x is equal to the secant of x. Determine a general expression for the non-permissible values in radians for this identity.
Okay, so in this particular case here, notice that with this identity that we've been given here, that there's no explicitly stated denominator. So it's not like I'm going to go to the denominator and set that equal to 0. What I got to do is I got to know enough to look in here and realize, okay, sine and cosine here, these two factors here, these two expressions, they do not come with any non-permissibles, but tangent does, and so does secant. And now let's just think about it a little bit. Okay, what is tangent? Well, tangent is the sine of that angle divided by the cosine of that angle. Okay, what is secant? Okay, secant is just going to be 1 over the cosine of that angle. So in this case here, because the denominator for both of these are the same, really all I got to do here is I got to solve this little thing. I cannot let cosine go to 0. If cosine goes to 0, that's going to cause problems for both tangent of x and secant of x. So here's what I got to solve for here. I got to do this in radians. Now let's think about this. Where does cosine become 0? Okay, think about the unit circle. Remembering that the cosine of an angle is associated with the x-coordinate of any point that's, of the point on the unit circle, but the x-coordinate of the terminal arm. Where does cosine go to 0? Where does the x-coordinate go to 0 as you go around? Well, it's going to be on the y-axis. That's where x goes to 0. And what angles do those correspond to? Okay, well, that's going to correspond, if you wrap this around, it's going to correspond to pi over 2 and 3 pi over 2. So x cannot equal pi over 2 or 3 pi over 2 plus n 2 pi, where n is an element of the integers. Okay, because I don't any whole number of rotations away from those 2 points there is going to leave me right smack dab in that same position, so I don't really want that. And just like a previous question here, actually I can streamline this a little bit because again those differ by pi, so I might just say pi over 2, x can't equal pi over 2 plus multiples of pi. Okay, where n, again, n pi, where n is an element of the integers. And that should be sufficient.
Simplify each expression to a single trigonometric function. 1 divided by tan x cosecant x.
Okay, so now we're going to simplify this and write this as a single trigonometric expression. What you want to bear in mind is that we're working through these problems here is that every step along the way, what we're doing is we're creating an expression that is equivalent to the one before it. So there's a couple of things we're going to have to pay attention to as we go through this. So I'm looking for an expression that can be rewritten in a different form, but is essentially equivalent to this. So if you think back to that little flow chart that I gave you there, first of all, you're going to look for Pythagorean identities here, and I don't see any Pythagorean identities here. Then I'm going to look for any adding and subtracting of fractions. I don't see anything there. Now I'm going to check for reciprocal identities. Now, that's typically going to be your cosecant or your secant there, your cotangent there. And in this case, I do have that cosecant. Okay, so this is the same as tangent of x multiplied by 1 over the sine of x. Now, I could write that as, like, bring that sine of x up into the numerator. I could. And actually, it won't change much of anything here, but I'm going to leave it down there for right now. There's no Pythagorean identities that have popped up. There's still no addition, subtraction. There's really no more reciprocal identities. There's no double angle identities, and so the very last thing I'm going to do is I'm going to rewrite that tangent in terms of sine and cosine. So this will become the sine of x over the cosine of x multiplied by 1 over the sine of x. And now, again, I look for any Pythagorean identities or whatever, but I also look for these canceling here. And notice that I get the sine of x divided by the sine of x. And so this will become 1 over the cosine of x. However, that is only true, okay, I just canceled that sine out there. That will only be true as long as the sine of x doesn't equal 0, which means that's only going to be true so long as x does not equal multiples of pi. Okay, where n is an element of the integers. So long as x isn't 0 or pi or 2 pi or whatever, because all of those are going to have signs of 0 there. And that's fine. Now, additionally, I'm dividing by a fraction. I'm dividing 1 by 1 over the cosine of x. Now, when I do that, I'm going to multiply by the reciprocal, and that's going to leave me with just the cosine of x. Now, this is an interesting result here, because cosine itself does not have any restrictions to it, but there are restrictions up here in the original. Part of that is coming from that sign that I just got rid of here, right? So I still have this little restriction here, x cannot equal n pi, where n is an element of the integers. But I've got another restriction here. Now notice here in the denominator, 1 over cosine of x. Well, 1 over cosine of x. This would be undefined if cosine was equal to 0. Now granted, 1 over that puts it up here and there's no longer an issue. But that little bit of algebra there aside, that's not the point. At this level right here, cosine can't go to 0. Here, cosine can't go to 0. And in that tangent, I can't allow that cosine to become 0 because it causes tangent to be undefined. So there is a restriction here related to cosine of x. Granted, it disappears here. But in order to maintain that equality all the way down, I have to address that here. So I also cannot let x equal, well, where does cosine go to 0? Well, it goes to 0 at pi over 2. Okay, actually, it goes to 0. I can even be, well, at pi over 2 plus n pi, where n is an element of the integers. Okay? Now, take a look at what I'm saying here. If you look at the coordinate plane here, I'm saying that x can't be here or here. Sorry, the angle can't be here or here. It also can't be here or here. So really what that is I'm saying that that expression is equal to the cosine of x, where x cannot be any multiple of pi over 2, where n is an element of the integers. And so that's my final expression. That's what that is equivalent to.
Cosine squared of x divided by the sine squared of x plus cos x multiplied by secant x.
Okay, for this question right here, this is a good question. It looks a little bit more complicated than the one that we just did, but it's actually not all that much more complicated. There are, however, a couple of different ways that you can approach this one. I have given you kind of an outline, a little flowchart to follow, and I will follow that for the first step here, but the more comfortable you get with identities and the way this sort of mathematics works here, the quicker you're going to get to approach the answer here. And I'll show you two different ways to do this one here. First of all, let's take a look at that flow chart there. The first thing I want you to look for was Pythagorean identities. And I don't really see anything here. I see some squaring, but I don't see that identity popping out, the +1 or the sine squared plus cos squared. They're not there. Is there any adding and subtracting of fractions? Well, yes, there is. I've got 2 here. The denominator here is just 1. Okay, so what I'll do here is I can make these things, I can give these things a common denominator of sine squared by simply multiplying this expression numerator denominator by sine squared. Okay? Now, yeah. Next thing we're going to do here is I asked, do I see any Pythagorean identities? Well, I do see a sine squared and a cos squared, but because of that cos x sine x, they don't actually add to 1 yet. That multiplication occurs before the addition, order of operations, and so I can't quite do that yet. Okay, do I see any adding and subtracting now of the fractions and whatnot? Any expanding, any, well, not really. You could look at this as factoring the cosine out. That is a possibility, but that's going to lead to kind of a dead end here. I'm more intrigued by the fact that there's a cosine squared and a sine squared there. So I kind of want to leave that cosine as being squared right now. Okay? Are there any reciprocal identities? Well, yeah, there's that secant in there. So the numerator could be rewritten as cosine squared plus the cosine of x times 1 over the cosine of x multiplied by the sine squared of x, and this is all over the sine squared of x. Okay, that's wonderful. Now, I'm still not seeing the Pythagorean identities. I've already done the adding and subtracting here. The reciprocal identities are gone and so on and so forth. But notice that I can do this little bit of canceling right here. Okay, and so this becomes the cosine of squared plus the sine of squared of x, and oh, I like that. Okay, now before I do this though, I can only cancel those so long as cosine does not equal 0. Okay, I can only get rid of that so long as I don't let cosine go to 0, and cosine is going to go to 0. Okay, when the angle is along the positive, the y-axis here. So I cannot let x be pi over 2 plus n pi, where n is an element of the integers. Can't allow that to happen. Okay. Now, this point here, so I've dealt with that, done my little canceling. I've addressed the fact that there's a bit of an issue there in terms of the value. Now I look at this as, are there any Pythagorean identities? Yes, cosine squared plus sine squared is equal to 1. Wonderful. Now I've still got this. X cannot equal pi over 2 plus n pi, where n is an element of the integers. Do I need to keep writing that? Yes, yes. If you stop writing it, it's no longer equivalent to any of the steps above here. Now, at this point here, there's no more Pythagorean identities, there's no more adding and subtracting, but there is a reciprocal identity, and I can just make this a little bit easier to look at by simply writing this as the cosecant squared of x. And again, I have to include that x cannot equal pi over 2 plus n pi, where n is an element of the integers. The reason I need to keep including this is because cosecant doesn't have that problem. All by itself, cosecant doesn't. But the original expression did. It did have that problem with it. I couldn't let x equal pi over 2. Okay? So in order to keep those equal, I actually have to state that restriction to put it there. Now, and that's correct. This is great. However, there is another restriction here, and there are this is a bit of a hard one to explain. You needed this one right here because that expression, the cosine, disappeared. And however, it brought with it this restriction. So I need to state that because it's kind of gone from this expression. However, there is another restriction here. I can't allow sine to go to 0, okay, now, because that makes cosecant undefined. Now, that restriction is right here. Like I'm looking at it. I already know that cosecant is like that. I don't really have to state it to make this expression equal to this one. So what I'm about to write here is not about making these things equal. It's about helping you get the mark, okay? And you really should, at this point, you also say, okay, this is also true as long as x does not equal multiples of pi, okay, where n is an element of the integers, because multiples of pi is going to be where sine goes to 0. And so there's your two restrictions here. And actually, we saw this before, that another way of doing this would be to say, okay, that means this is equal to the cosecant where x cannot equal multiples of pi over 2. And that actually covers both of those restrictions together. Now, just so that you're kind of clear on how this works, I want to show you just really quickly one other little approach to this. If you take a look at the original identity here, the other thing that we could have done is said right away here is just take a quick look at this. This is only when you get really comfortable with this, comfortable enough that you can take these kind of shortcuts. Cosine squared over sine squared, sorry, I'm buckled here, is cotangent squared. And then the more comfortable you are with this, the more obvious this gets here. Cosine of x multiplied by the secant of x. Well, secant is the reciprocal of cos. That's always going to be 1. Okay, so this will be plus 1. And then that is a Pythagorean identity. And so you could jump immediately to the cosecant of x here. Now, remember, when you make this equal to 1, though, this is where you would have to state, okay, x cannot equal pi over 2 plus n pi, where n is an element of the integers, because I got rid of the cosines. And then you would write that down here. X cannot equal pi over 2 plus n pi, where n is an element of the integers. And then Again, that is necessary because I lost the cosine, but then again, to get the mark, I would also include x can't equal n pi, where n is an element of the integers, and so on and so forth, okay? So, but this is really once you start getting more comfortable with the way identities work. I wouldn't suggest that to start off with, because if you start looking for those little shortcuts too quickly, it's often the case that people will apply them wrong. Okay, so just be careful.
Cosine of theta divided by 1 plus the sine of theta plus the tangent of theta.
Okay, so in this case right here, we're going to follow that little procedure that I've given you there. The first thing we're going to look for here are Pythagorean identities, and I don't see anything. Okay, next thing I'm going to look for, is there any adding or subtracting or whatnot? And yes, there is. I've got these fractions here that I can add. Okay, this is like 10 over 1. And so the common denominator here is going to be 1 plus sine. So, 1 plus sine, multiply that there in order to get common denominators. And now what I'll write here is my numerator will be the cosine of theta plus the tangent of theta times 1 plus the sine of theta all over 1 plus the sine of theta. Good. All right, now once that's done, I ask myself, okay, do I now see any Pythagorean identities? No, I don't. Do I see any adding and subtracting of fractions and whatnot? No, I don't. Any obvious factoring and whatnot? No. Please don't be the person who tries to cancel these out, okay? Because you just added those together. Those don't cancel. There's an order of operations mistake being made there, okay? You would need, that bar there implies brackets. You'd need to do the addition here before you could do that kind of division. And you can't at this point because they're unlike terms. Okay, do I see any reciprocal identities? That's the cosecant, cotangent, secant, and I don't. Oh, this is getting a little rough here. No double angle identities, but I can now write these things in terms of sine and cosine. That's not always the best place to start, but as long as you've kind of eliminated all those other options, that's actually not too bad. And so this is going to be 1 plus the sine of theta all over 1 plus the sine of theta. Okay, now, it's kind of a weird position to be in, but what I'm doing here is I'm trying to be really consistent with this method here. Do I see any Pythagorean identities? No. Do I see any fractions that I could now add? Yeah, I do, right up here in the numerator. Okay, this is like cosine over 1, and now this guy's got a denominator of cosine, so I could multiply numerator and denominator here by cosine. Okay, and I will get the cosine squared of theta. Okay, and now this is all going to be over cos theta. And actually, I'm going to do one other thing here at this point, and you'll see why in a second here, but that second step in my procedure is really just about like algebra that you're going to do. And there's a little bit more algebra here. Not only can I make this cosine squared over cosine, but I can distribute that sine through. And so this will become sine of theta plus the sine squared of theta. So I've done a couple things here. This is still all over 1 plus the sine of theta. Okay. Now, are there any Pythagorean identities here? Yes. Cosine squared plus sine squared is equal to 1. Now, a couple of things here. Notice also I've got this fraction over a fraction. I can multiply by the reciprocal. So I'm going to, first of all, I'm going to make that cosine squared plus sine squared 1. So the numerator becomes 1 plus sine theta. And then over cosine of theta multiplied by really 1 over 1 plus sine theta. So I get 1 plus, whoops, the sine of theta there. Oh, this is wonderful now, and I hope you see it here. Now, 1 plus sine of theta cancels, and so I'm left with 1 over the cosine of theta. Now, I can only cancel that, though, under the stipulation here that the sine of theta does not equal 0. Oh, sorry, negative 1. 1 plus the sine of theta can't equal 0, which means the sine of theta can't be negative 1. Well, where does that occur? Sine of theta equals negative 1 at 270 degrees or 3 pi over 2. So I'm saying here theta cannot equal 3 pi over 2 plus n2 pi, where n is an element of the integers. So there's my restriction right there. There's my answer, and actually I've got it reduced down quite nicely. I am, however, going to go one step further, and I'll bring this all up to the top again, okay? Because I can rewrite 1 over cosine of theta a little nicer. I can make that equal to secant of theta. And again, where theta cannot equal 3 pi over 2 plus n2 pi, where n is an element of the integers. And so there's my restriction. Now, I need this part right here. I'm going to keep saying this because I hope that it starts to make sense to everybody. I need to state this. Okay, this restriction came from a part of that identity that I got rid of. But it was still part of this identity. So in order for this to be equal to this, not just equivalent, but equal to it, I need to identify the parts that went wrong here. And so I need to include that. Now, that's true for the answer here, but if you want to get the full mark here, I suspect that most teachers are going to ask you to include the restrictions on the secant here. And in this case here, secant is undefined when cosine goes to 0, and that's going to be at pi over 2. So theta can't be pi over 2 plus n pi, where n is an element of the integers. Okay, and so there's our final answer there.
The sine of x plus the cosine of x multiplied by the cotangent of x, all divided by the cotangent of x squared plus 1.
All right. For this last one out of this section here, I like this question. It's got something to consider in here, something that I don't want you to stumble on, I want you to be aware of. So we're going to set this equal to, okay, so the first thing we're going to look for here is, are there any Pythagorean identities? And the answer is yes, that denominator has got a Pythagorean identity in it. Cotangent squared of x plus 1 is going to equal the cosecant squared of x. Perfect. So we've dealt with that. Now, the next thing we're going to do here is we're going to take a look at this and say, okay, are there any Pythagorean identities now? And the answer is no. No, not really. Please don't be the person who says and go, cosecant squared of x equal to cotangent squared of x plus 1. Oh, this is equal to cosecant squared of x. Like, don't keep bouncing back and forth there. Oh, yeah, you could do that forever. There's no Pythagorean identities. Okay, is there any obvious algebra that I can do here? Any factoring, expanding, and whatnot? Well, no, not really. Are there any reciprocal identities I can deal with? And in this case, yes, there are, specifically that cosecant. So this becomes the sine of x plus the cosine of x. Now, in this particular case here, I can kind of see what's going to happen here in a second. So I'm going to leave this as the cotangent of x. There might be some temptation here to write this as 1 over tangent. But with all the sines and cosines here, I think eventually I'm going to write that in terms of sine and cosine. But this this cosecant squared here is going to become 1 over the sine squared. Sorry, I could have done that a little bit better here. Hold on. 1 over sine squared. Okay. Now the next thing I'm going to do is deal with that 1 over that sine squared there. So that's my little bit of algebra here. So I'm going to end up multiplying everything through here by sine squared. And so this will become the sine squared of x multiplied by the sine of x plus the cosine of x times the cotangent of x. Now, and I might distribute that in a second here. I probably won't. I'm going to kind of clean this up first without making it messy with that sine squared going through. However, notice that what I've done here is I've gotten rid of this 1 over sine squared. I no longer have an expression here that's dividing by sine squared. So what I got to do here is I have to identify what I've lost here. There is a non-permissible here that's no longer exists here. Okay, sine can't go to 0. Okay, which means x cannot equal, if we do this in radians here, x cannot equal multiples of pi. Okay, or else sine goes to 0, sine squared goes to 0, cosecant goes to 0, and so on. Now, what's interesting about this, though, everybody, is we take a quick look up here. I can't allow sine squared to go to 0, but watch this. There might be a question here as well, what about the cotangent squared of x plus 1? I also can't let that go to 0. But that means that the cotangent squared of x can't equal -1. And the answer is, the truth is, that never happens. Cotangent squared can't ever equal -1, not unless you start talking about imaginary numbers. And so this isn't even an issue. The denominator here doesn't go to 0. The only place that we have this non-permissible coming up here is because cotangent itself has a non-permissible with it. And that's actually what we're addressing here. Okay, and that's going to take into account this cotangent as... sorry, not exactly, sorry. But that's where that's coming from. Now, let's keep going here. Do you see any Pythagorean identities? No. Is there any obvious algebra here that we can do? Well, not at this point. There's none of the double angles or whatever, but what I'm going to do is I'm going to write everything now in terms of sine and cosine. And I could see that that was going to happen here before, so this becomes the cosine of x over the sine of x. Okay. Now, at this point, I could, I could add these two fractions together here. And so this is going to get me sine squared of x. And what's nice is this becomes the sine squared of x. This is over the sine of x plus the cosine squared of x. I'm sorry, I have said before that you need to keep writing this and then I stopped doing it. We need to include this restriction all the way down to indicate that every step is equivalent to the one above it. But now, sine squared plus cosine squared, there's my identity. It's 1 over the sine of x. So 1 over the sine of x. Again, x cannot equal n pi, where n is an element of the integers. Now, sine squared of x over the sine of x, one of the signs cancels, and I get the sine of x at the end here, where x cannot equal n times pi, where n is an element of the integers. Now, I have already addressed, like I canceled a sine here, but I've already addressed that issue that sine can't go to 0, and that's where with the n pi here. So that's already been dealt with, and so that's the restriction that we need.
Verify the following identities with the angle provided. The cosine of x multiplied by the sine squared of x plus the cos cubed of x is equal to 1 divided by the secant of x when x is equal to pi over 3.
Okay, now in this case, we're moving towards the proving of identities. We're going to take a quick second here and talk about verifying identities, because I suspect you're going to get asked to verify identities as you go along here. What a verification is just really quickly to check to see if it could possibly be an identity, okay? So, for example, when we plug in pi over 3 into this, if the left side and the right side are not equivalent to each other, it's not an identity. I mean, it's that dead end right there. But in this case here, if they are equal to each other, that doesn't mean that it is an identity, just that it could be an identity, okay? So what we're doing here is we're going to draw a line basically from the equal sign down. We don't move things from one side to the other, not when we're dealing with identities. The ability to move something from one side to another in an equation is because of the property of equality, okay, of what that equal sign tells us about this the expression here that we're writing. Now, but if we don't know whether if that's equal or not, then we can't move things across there. So we're gonna separate that out, plug the pi over 3 in, and hope that independently of each other, these two sides give us the same result. So we plug pi over 3 in. So this will become the cosine of pi over 3, the sine squared of pi over 3, plus the cosine cubed of pi over 3. And on the right-hand side, it'll be 1 over the secant of pi over 3. Okay, now, this is going to be equal to, well, okay, the cosine of pi over 3, think back to your unit circle here, that's going to be 1/2. Sine of pi over 3 is going to be root 3 over 2. I will square that afterward. Now, okay, now that I've got it, I'll square it. I'll get to that in a second. And then we've already stated here that the cosine of pi over 3 is 1/2, and we're going to cube that. Over here, 1 over, okay, well, secant is the reciprocal of cosine of pi over 3. I already know that the cosine of pi over 3 is 1/2. So the reciprocal of it down here is going to be 2. So the whole expression becomes 1/2, but it's really 1 over the secant of pi over 3, and that secant of pi over 3 is 2. That's kind of done. There's not much more I can do with that 1/2, but I got some work I can do over here. This is still going to be 1/2 multiplied by, okay, well, root 3 over 2 squared is going to be 3 over 4. And then 1/2 cubed will be 1/8. When I multiply those together, I'm going to get 3/8 plus 1/8 gives you 4/8. Whoops, running out of room there. And then that reduces down to 1/2. And so there we go. That's true. The left side is independently equal to the same value as the right side. We have been able to verify that this could possibly be an identity.
The secant squared of x minus the sine squared of x is equal to the cosine squared of x plus the tangent squared of x when x is equal to pi over 4.
Okay, as we did with the previous question, first I'm going to do is draw that line there so that the left side and the right side are separate. And now we're going to put that pi over 4 in. So we get the secant squared pi over 4 minus the sine squared of pi over 4. On the right hand side it will be the cosine squared of pi over 4 plus the tangent squared of pi over 4. Oops, sorry, you can't see that. Okay, now let's take a look at what these expressions are equal to. Okay, well, secant is the reciprocal of cosine. What is the cosine of pi over 4? Well, the cosine of pi over 4 is root 2 over 2. So this is actually going to be 2 over root 2 squared. And I know that can be written a little bit differently, but I'm just going to, for the sake of people who maybe get kind of overwhelmed with what you're seeing here, let's just do this a bit at a time here. So secant, just think it through, is the reciprocal of cosine. Cosine of pi over 4 is root 2 over 2. So this is going to be 2 over root 2. The sine of pi over 4 is the same as the cosine of pi over 4. That's what's interesting about 45 degrees or pi over 4. So this is going to be root 2 over 2, and that'll be squared. On the right hand side, well, we've already addressed this. The cosine of pi over 4 is root 2 over 2. So this will become root 2 over 2, again squared, plus, and I like this one because the tangent of pi over 4 is 1. And we're going to square that. That was the easy part of that. Okay. Now, down here, we're going to perform the squares before we do the addition and subtraction here. Okay, that's just order of operation. So 2 over root 2 squared, that's going to become 4 over 2. That's going to be nice. That'll simplify nicely. This is going to become 2 over 4. And then over here, this is going to become 2 over 4 plus 1. Now, what might we do here? Well, okay, I can see that I have fractions here. What I'm going to do here, I'm just going to be lazy about this, okay? 2 over 4, I know I can simplify 4 over 2. I know. But 2 over 4 is going to become 1 over 2. And you see, by just simplifying that 1, I've got common denominators. And so 4 minus 1 all over 2, this is going to be 3 halves. Okay? Over here, I'm going to change this. This will become, what do we got here? This will become, oh, sorry. I can simplify this first before I start putting these together. This will become 1/2 plus 1. And, I mean, 1 can be written as 2 over 2, and so that itself becomes 3 over 2. So again, here we go. Independent of each other, we've been able to show that the left side and the right side are equivalent to each other. So yeah, we have verified this could be an identity. I haven't proven that it's an identity. All I've demonstrated is that it could be. This warrants further investigation.
Prove the following identities. Sine of theta minus the cosine of theta divided by the sine of theta is equal to the cosine squared of theta minus the cotangent of theta plus the sine squared of theta.
All right, now we're going to start proving identities. And I know this isn't everybody's cup of tea, that this is something that causes a bit of anxiety for people here. We're going to try to really follow that procedure that I've given you earlier here, and hopefully you'll see how it works quite nicely here. So, proving identities. I do not know that the left side and the right side are equal. So I can't start bringing stuff over from one side or the other because that's the property of something that I know to be an equation. And I don't know that this is actually true. So I have to show independently that the left side and the right side are the same. So what I'm going to do here to start off with here, okay, is let's take a look at the left-hand side. Do I see any Pythagorean identities? No. Do I see any adding or subtracting of fractions, factoring or expanding or another? And the answer is yes, I do, except that this is probably one of the less obvious bits of expansion here, okay? Let me show you here. Actually, let me come up here. If I gave you A times B plus C, most of you would know right away that means A times B plus A times C. I think that's pretty clear. You're going to distribute that A through. But that is equally true if I had 1 over A times B plus C. I would distribute the 1 over A through, so it becomes B over A plus C over A. It's the exact same property that I'm making use of here. It's just that the expression or the factor up front here is written in the form of a rational. Well, that's exactly what we've got here. Sine theta minus cos theta over sine theta is the same as 1 over the sine of theta multiplied by the sine of theta minus the cosine of theta. And so I can distribute this thing through to get the sine of theta over the sine of theta minus the cosine of theta over the sine of theta. Okay? Now, I'm going to keep going with this. Normally what you would do with an identity, by the way, is you would take a look at the more complicated side and you would reduce it to an expression that you're hoping would be equal to the simpler side. Now in this case I'm starting on the left hand side here because anytime you got a rational, that is just more complicated, okay? Over here you might argue that this is more complicated because of the number of terms I've got, but there's no fractions here to deal with. This is the fraction one, so I think most of us would agree that's probably the harder one. Now here sine of theta over sine of theta is going to become 1. And cosine of theta divided by the sine of theta is the cotangent of theta. Now I write it like that because I see a cotangent over there and I am curious as to whether that's going to work or not. Now this is equal to this. I cancel the signs there. So this is true, comma, so long as, oh sorry, not x. Sorry, we're using theta. That's true so long as theta does not equal any values that force sine to go to 0. And that is going to be at multiples of pi. Now, I don't really need to write that because there is a sign here. Cotangent still has that same restriction, so I don't really need to state it. But it's not a bad habit to get into here, okay? I canceled something out here that probably carried some sort of restriction with it. I should identify that. Over on the right-hand side, that's about as simple as I'm going to get that, because 1 minus cotangent isn't a Pythagorean identity, and if I write it in terms of sine and cosine, I'm just going to go back up to there, so I'm not going to gain anything by it. On the right-hand side, are there any Pythagorean identities? And yes, there are. Cosine squared plus sine squared is 1. And so immediately we get the 1 minus cotangent of theta popping out. Now, do I have the same restrictions? Okay, like does the right-hand side have the same restriction? And the answer is yes, it does. And the reason it does is because cotangent all by itself, remember back to when we were talking about restrictions here, not only are you looking at where the denominator goes to 0, you're also looking for tangent, cotangent, cosecant, secant, because those four also carry their own restrictions. And cotangent also has the restriction, okay, that theta here can't be multiples of pi. And so there we go. The left side and the right side are equivalent without independent, okay, of each other. So that is an identity.
The tangent of theta minus 1 divided by the cotangent of theta minus 1 is equal to the negative 1 over the cotangent of theta.
Okay, here we go. Let's take a quick look at this identity here. Now, remember, we're going to work left side and right side independent of each other. And I'm going to typically start with the more complicated side. However, in this case, I'm not going to. And just let me explain myself with this real quick here. I am going to spend most of my time working on that left-hand side because it is by far the more complicated. But just look at the right-hand side. This is 1 over cotangent. There's really not much going on there. However, I cannot foresee myself algebraically working this down and putting a reciprocal identity in the denominator, okay? Or that kind of cotangent in the denominator. I know that cotangent is the reciprocal of tangent, so I'm just going to write this as negative tangent. It seems far more likely that I'm going to reduce this down to a tangent, not a 1 over a cotangent. That seems like just an extra little step that they want me to do here. Now, however, though, that introduces a couple of issues here. So notice that cotangent has a restriction. I've kind of gotten rid of the cotangent. It's not there anymore. So this is only equal so long as theta does not equal, well, where does cotangent go to 0? Sorry, not 0, my mistake here. I've gotten rid of the cotangent, and the cotangent has its own set of non-permissibles with it. Where was cotangent undefined? And cotangent all by itself is undefined at n pi, where n is an element of the integer. Okay? Now, I might want to go one step further here and identify, okay, well, at the same time here, I've got rid of the cotangent. Where did the cotangent go to 0? Well, cotangent goes to 0 at multiples, sorry, at pi over 2 plus multiples of pi. Okay? So, got a couple things going on here. First of all, cotangent is undefined. I've gotten rid of the cotangent. I'm no longer writing it. It was undefined at multiples of pi. Okay, it goes to 0 when it's pi over 2. Now, you'll notice here that just because of the way this works here, I've also got the restriction for tangent implied in there, because tangent is undefined at that pi over 2 plus n pi here. But because of those, putting those together, I could simplify that by simply saying theta cannot equal multiples of pi over 2. Anyway, so I've dealt with a few things here. Now I'm going to spend most of my time working on that left-hand side and seeing if I can't get it to look like negative tangent of theta. Well, on the left-hand side here, do you see any Pythagorean identities? No. Do you see any fractions that you could add or subtract? No, not right now. Any reciprocal identities? Yeah, but just that one there, 1 over tangent. And to be honest here, I don't know that that's actually going to help me the way I want it to. Actually, you know, let's try that. Because cotangent is a reciprocal identity, so this would be tangent of theta minus 1 over, this is like 1 over the tangent of theta minus 1. Now, do we see any Pythagorean identities? No. But do I see any fractions that I can add or subtract? Yeah, that denominator there. So this becomes the tangent of theta minus 1 over 1 over, sorry, the denominator here becomes the tangent of theta, and this will become minus the tangent of theta. Okay, that's kind of cool. Now, this is in the denominator here. I'm going to multiply by the reciprocal here. So this is going to become the tangent of theta minus 1 over 1, really, multiplied by the tangent of theta over 1 minus the tangent of theta. Okay? Whoops, sorry, I'll rewrite that. I put a parenthesis there that I really didn't mean to do that. So this becomes the tangent of theta over 1 minus the tangent of theta, and that's all part of that second factor there. Okay, now interesting thing happens here. Tangent of theta minus 1, 1 minus the tangent of theta. Now if it's not abundantly obvious to you, one of the things you can do here is notice that this expression here doesn't look good. It kind of looks kind of bad. We like to have things where the constants are kind of, whatever we're adding or subtracting at the end here, it's at the end here. So this is like the tangent of theta minus 1 multiplied by the tangent of theta. I'm going to factor a negative out of that, and what that'll do is make that tangent positive, make the 1 negative. And now those will cancel. So really, once I got past the reciprocal identity here, Okay, this has all been about just that little bit of algebra work here. Now there was something that happened here. As soon as I multiplied by the reciprocal, I got rid of that tangent in the denominator. Now I don't have a lot of room on this side here, unfortunately, but there was a restriction that popped up here. I got rid of the issue where tangent could become 0. Okay, down here, if tangent is 0, this becomes undefined. Well, tangent goes to 0 wherever sine is 0, and that's going to be at multiples of pi. And so what we've got here is the final result here is going to be negative tangent of theta, which is perfect. I have this result here because of up here. Okay, I can say that theta cannot equal multiples of pi, where n is an element of the integers. Okay, because as soon as I multiply by the reciprocal, I've moved that denominator up. So I've gotten rid of that non-permissible, so I have to state that. If you take a look at this, notice that tangent has its own little bit of non-permissibles here. Remember that for tangent, theta can't be equal to pi over 2 plus n pi, where n is an element of the integer. So that carries through here. So now when we take a look at this, we might think, look at this, this is amazing. Because remember, I can rewrite all of this as negative tangent of theta, where n cannot equal, okay, n pi over 2, where n is an element of the integers. And that is exactly the same as the right-hand side here. However, there's one little issue here. Notice that what I did here is I canceled tangent of theta minus 1 and tangent of theta minus 1. I can only do that as long as tangent does not equal 1. Okay? Which means, oh, sorry, not n can't equal that, theta can't equal that, which means there's another restriction here. Okay? Theta on the left-hand side cannot equal pi over 4 plus n pi, where n is an element of the integers. So it turns out this is not exactly an identity. It's not 100% correct here, because this one has this added restriction that the right-hand side doesn't have. So this is not truly an identity. Okay, and we've been able to prove that that's the case. So the thing that we might want to say at the end of this, and I highly doubt that you would get a situation like this where a teacher would ask you to take it this far, but I do want you to recognize here that this is not truly an identity, because the left side and the right side are not always equal to each other regardless of the value you plug in. The best thing that we can say here is that the tangent of theta minus 1 over the cotangent of theta minus 1 is equal to negative 1 over the cotangent of theta, so long as theta does not equal pi over 4 plus n pi, where n is an element of the integers. Okay, for all other values, left side and the right side will be the same. They'll even be undefined at some specific values, but not here. This is where they differ. Okay, and so that's the best you can say in the scenario like this.
The sine of theta plus the cosine of theta, all squared, is equal to 1 plus 2 times the sine of theta times the cosine of theta.
Okay, now let's see what this one holds. Notice there's no denominators here, and notice there's no tangent, cotangent, cosecant, or secant, which means there's nothing here that's non-permissible. So that actually gives us a little bit of confidence going on here. Now, do you see any Pythagorean identities? Well, no, not really, but there is some obvious algebra here. I've got this square. So I'm going to start on the left-hand side here, and I'm going to square that. I'm going to expand that out, and that's going to get me the sine squared of theta plus 2 sine theta cosine of theta plus, actually I didn't give myself enough room for that, okay, plus the cosine squared of theta. Now, if you're wondering where that 2 sine theta cosine theta came from, it's because you're not properly squaring this. Okay, remember, you have to distribute this out. You cannot just take and square the first term, square the second term. Okay, you have to multiply sine theta plus cos theta by itself. Now, in my second step here, I noticed that there is a Pythagorean identity. Sine squared plus cosine squared is equal to 1. And so we're left with 1 plus 2 sine theta cosine theta. And so now, yeah, we've seen that the left side is equal to the right-hand side. because that was 2 sine theta, 1 plus 2 sine theta cosine theta. So yeah, that is an identity.
1 plus the sine of theta all over the cotangent of theta plus the cosine of theta is equal to the tangent of theta.
All right, now let's take a quick look at this one. And obviously we're going to spend all of our time here on the left-hand side, trying to see if we can make this look like the right-hand side. However, you should see right away here, we're going to run into some issues with the non-permissibles. On the right-hand side, okay, we know that theta here cannot equal, can't equal pi over 2 plus n pi, where n is an element of the integers. Okay, that's just the restriction that normally comes along with tangent. Now let's take a quick look over here. On the left-hand side here, we've got a couple other things going on here. First of all, we've got the cotangent down here. Now cotangent carries with it its own set of restrictions here. First of all, we know that theta won't be able to equal you know what? Actually, I think what I'm going to do with this one is I'm going to just follow this one through here, then we're going to come back and take a look at what happens here. On the left-hand side, let's just simplify it first, and then I'll let the the restrictions kind of fall out from there. Notice that there's no Pythagorean identities. Okay. There's no real obvious algebra here. What I'm going to do though is, instead of writing this as 1 over tangent, I'm going to write this in terms of sine and cosine. In this particular case here, I think that might be the simplest way to go about doing this. And so this becomes the cosine of theta over the sine of theta plus the cosine of theta. Okay? Now, do I see any Pythagorean identities? No. But I do see some algebra that I could do here. I can add these two fractions together. So I'm going to get 1 plus the sine of theta, there's my numerator, over, and this will be the cosine of theta, plus the cosine of theta times the sine of theta all over the sine of theta. Okay? Awesome. Now, do I see any Pythagorean identities? And the answer is no, I don't. Do I see any obvious algebra that I could do here? And yeah, I do. Notice I've got a common cosine to the numerator, to the numerator here down in the denominator. So this will be 1 plus the sine of theta over the cosine of theta, and then I'm going to be left with 1 plus the sine of theta over the sine of theta. Oops, sorry, can't see that. Okay, now look at this, 1 plus sine theta, 1 plus sine theta. Now what I'm going to do here is I'm going to multiply by the reciprocal here, because I'm dividing by a fraction, so I'll give myself a little bit more room here. This will become 1 plus the sine of theta over the cosine of theta, and I'm going to multiply by the sine of theta over 1 plus the sine of theta. Now, as soon as I do that, I'm going to run into a situation here, because here I was dividing by the sine of theta, and now all of a sudden I've gotten rid of that. Now I'm multiplying by, so there's a restriction here. I can't let the sine of theta go to 0, which means I can't let theta be n pi, where n is an element of the integers. So there's my first issue. Okay, and notice that this restriction for the left-hand side does not exist on the right-hand side. So this is not technically going to be an identity. I'm going to have to rewrite this again at the end to identify the relationship here, the true relationship here. Now, addition to that, 1 plus sine over 1 plus sine is going to cancel, and so I'm going to be left with here the sine of theta over the cosine of theta, so long as theta does not equal n pi. I've already dealt with that, but there's going to be another restriction here. Notice that, and actually I'm going to have to give myself a little bit more room here to write this out. Sine of theta can't be equal to -1, because if it is, then 1 plus sine of theta goes to 0. Now, where does the sine of theta become -1? And the answer is at 3 pi over 2. So 3 pi over 2 plus n 2 pi, where n is an element of the integers. So I've got these two expressions, n pi and 3 pi over 2 plus n 2 pi, where n is an element of the integers. So that's, again, another restriction that does not exist on the right-hand side. Okay, actually I should say that's not entirely true. Sorry, I had to look at it twice here. Actually, because this is n pi, that actually does exist there, that 3 pi over 2. This one does exist, just in part. And so now sine of theta over the cosine of theta, that is going to be the tangent of theta. And here we go. So the restrictions are it can't be n pi. Okay. Now, because cosine is in the denominator and cosine is going to be 0 at pi over 2 and 3 pi over 2, what I could actually do here is say that it can't be n pi. It also can't be pi over 2 plus n pi, where n is an element of the integers. And that actually is going to encapsulate that restriction as well. Okay. And we've seen this before. This basically means it's going to be tangent of theta, where theta cannot equal, well, we're essentially looking at multiples of pi over 2. Okay, pi over 2, n pi, 3 pi over 2, and so on, where n is an element of the integers. Again, the restrictions are not the same. This is only at pi over 2 plus n pi. So this one here has restrictions on the y-axis. This one here has restrictions on the x and the y-axis. So really, what we got to say here is this is, sorry, right here, my mistake here. This is not truly an identity. Okay, this is not truly an identity. To make this an identity, what I would have to do here is state, okay, what this should say is 1 plus the sine of theta over the cotangent of theta plus the cosine of theta is equal to the tangent of theta if we include the restriction here that theta cannot equal n pi, where n is an element of the integers. If we exclude this set of angles here, then every other possibility that I can plug in there would make this side equal to this side. Okay, and that is actually a better way of writing that original statement.
3 times the sine of theta minus 1 divided by 3 sine squared of theta minus 7 sine theta plus 2 is equal to 1 divided by the sine of theta minus 2.
All right, now the final one that we're going to look at is this guy right here, and I like this one. Okay, I like this one here. We're going to split this up, and obviously I'm going to spend most of my time working on the left-hand side here, but I'm going to take a look at that right-hand side as well here, just for a second here, just to identify the non-permissible over here. Notice in this case on the right-hand side that I cannot allow, the sine of theta cannot be allowed to equal 2. But the truth is, that never happens. Okay, sine of theta never does equal 2. So in other words, this is good all on its own. There are no restrictions on the right-hand side, which is great. Now let's go to the left-hand side here. Do you see any Pythagorean identities? Well, I see a sine squared, but that actually looks more like a quadratic statement than anything else here. So no, I'm not seeing a Pythagorean identity. What I am seeing, though, is some obvious algebra that I'm going to have to do here. I'm going to have to do some factoring. And when I take a look at this, I'm going to need to break up that coefficient of 3 there into 2 factors, so that'll be 3 and 1. So this will likely be 3 sine theta, sine of theta. And then I need these two values, the last two, to have a product of 2, and the middle to have a sum that's negative. So I suspect these two are both going to have to be negative. That way they cancel and get positive there, and then they combine to get the negative there. And then, yeah, this is going to have to be 2 and 1. There you go. It have to be 2 and 1. Perfect. And so now I know that those two are going to cancel, and this will become 1 over the sine of theta minus 2. However, that only happens, okay, that only happens so long as the sine of theta does not equal positive 1, whoops, it's not 1/2, sorry. Not 1/2, but 1/3. Okay, so this is only true so long as the sine of theta does not equal 1/3. Now, I can find out what the angles are that correspond to that. Actually, you know what? My calculator is nowhere to be found. I will use my phone. Okay, and we will find out what angles those are. Just got to go to my calculator. So I'll just put that there. So I'm going to make sure, first of all, that I'm in radian mode. And the reason why I want to be in radian mode is because I've been in radian mode for everything here. And what we're going to do here is, this will be true. I want to figure out where sine of theta goes to 1/3. So that will be the inverse sine of 1 divided by 3. So my first answer to the nearest 100, let's say, is 0.34. That's in the first quadrant. Sine is positive in the first quadrant. So I'm going to want to figure out what that second quadrant angle is as well. So bring that over to the nearest hundredth, that's 2.80. So the answer is then this is going to be 1 over the sine of theta minus 2, so long as theta does not equal 0.34 or 2.80 plus n2 pi. Whoops, sorry, that's at the end there. Where n is an element of the integers. And so once again we run into a situation here where this is not truly an identity, because there are values where they are not equivalent. There's a values where the left-hand side is undefined, where the right-hand side isn't. So then how would we rewrite this in order to kind of get around that? Well, what we would do is we would say, oh, okay, that means that it has to be written like this. The 3 sine theta minus 1 over 3 sine squared of theta minus 7 sine theta plus 2 will equal 1 over sine of theta minus 2, so long as theta is not allowed to equal, we just figured this out, 0.34, 2.80 plus n2 pi, where n is an element of the integers. And that now covers it. This is now going to be always true.